Hello, everyone. I'm going to record our first lesson for remote teaching for discrete math. So this is on section 3.7, mathematical induction. And I hope you're all doing great and safe at home with friends and family, and everybody's healthy. But let's talk about induction. So this is the first kind of proof we're going to see that's not too formal. All the proofs that we're going to see in this this course are based on those propositions and logic tables and the laws of logic that we've learned in the last few sections. But those were kind of very formally done with sort of giving justification at every step. It was very abstract. Now we're going to sort of prove a few mathematical expressions, and sort of we're not seeing sort of justification at every step, but that's the basis, and I'll try to point it out as we're working through it. It's the basis of kind of all these proofs that we're doing, all right? So the principle of mathematical induction, says that if P of n is a proposition over the positive integer, so this is a proposition over a universe, which means n could be different values. So it's the proposition of the universe of positive integers. It says that if P1 is true, so the proposition is true for n is 1, and for all n is bigger than 1, Pn implies Pn plus 1, then P of n is a tautology. Okay, so that means that sort of in order to prove this proposition Pn is true for all values of n, which means a tautology, then you need to show these two steps, right? So we call this the basis step when you're looking at P1. And we'll see as we work through the examples that the value of n is 1 is flexible, it's not fixed. It depends on the problem that you're working on sometimes. So kind of, if we're talking about positive integers, we want to look at n equals 1. But sometimes we can extend this to non-negative integers, so we could start with n is 0. Sometimes our expression doesn't start working, doesn't start being true until n is a value that's larger than 1, until n is 2 or 10 or 12. So we'll see through the example as we work through them. And then the induction step right here, basically this says that if Pn is true, then Pn plus 1 is true. Okay, so often induction is sort of compared to like a ladder or a domino. So it says that I'm going to show that P1 is true. Right, so my expression, whatever it is, which in a few cases is going to be a formula like we're going to see in the first example. And I know that if I know that Pn is true, therefore Pn plus 1 must be true, then it kind of works like a domino, because then I know that if I start with something true, I know P1 is true, then P2 is going to be true by this induction step, okay? And I know that if P2 is true, then P3 is going to be true by this induction step. So kind of this induction step is proved in general for any value of n. So it works for any sort of n plus 1. So if you know, it works for 1 and 2, 2 and 3. It works for, if k is true, then k plus 1 is true. Okay? And basically you can see this is a bunch of chain rules, right? When we're looking at the laws of logic, we know that if P1, therefore P2, and if P2, then P3 work, then you know P1 is going to lead you to P3, right? So you can sort of basically do a bunch of chain rules that kind of lead you into, if I know P1 is true, then that's going to eventually lead me to Pn is true regardless of whatever n is. So that's kind of how it works in this ladder or this chain or domino effect. All right, so let's look at how it actually works in practice. That's kind of those laws of logic, underlying theory behind why induction works. And now we're going to make it work for a few examples. So let me pick a bigger brush. That's better. I don't like red. Let me go with blue. There we go. That's better. Okay, so example 1 says, prove by induction. I want to prove that the sum of positive integers 1 to n is equal to n times n plus 1 over 2. All right, let me erase this. It's bugging me. There you go. So let's rewrite this. So it says the sum of positive integers 1 to n. So that means I have 1 plus 2 plus 3 plus ... all the way to n. So that's the sum of the positive integers 1 to n. And I want to show that this is equal to n times n plus 1 over 2. Right. So this is a sum that you've probably seen before from other classes. This is like an arithmetic sequence. You can sort of figure this sum with the sum for arithmetic sequences, or you can sort of just figure it out by inducing it. That's where induction comes from. But sort of induction in our sense is a bit more formal than kind of just guessing that that's going to be, or hypothesizing. All right, so we have our 2 steps that we need to do with induction. All right, so let's look at the basis step. So the basis step right here says that we want to look at P1. Okay. We want to look at P1. So our P, when we talk the proposition, our Pn is this, is the proposition that says that 1 plus 2 plus 3 all the way to plus n is n times n plus 1 over 2. So when I say P1, I'm plugging in n is 1 in both sides of this expression, right? So when I plug in n in this sum of numbers, the 1 means that this sum of positive integers from 1 to n is going to stop at n. So if I'm plugging in 1, it's going to stop at 1. So it's sort of basically just 1 on the left-hand side, because you're doing 1 plus nothing because you already reached the end, okay? And then here we're going to plug 1 into n, so we get 1 and 1 plus 1 over 2, so that simplifies to 1, okay? So the basis step works, right? All right, now let's look at how the inductive step works. All right, so the inductive step, so what it says, this proof by induction method says, is that I'm going to look at 2 different values for my proposition P, okay? I'm going to look at Pn. I'm actually going to use K, right? And the reason I'm using K and why K is often used is you're trying to prove this proposition with n showing. And I sort of don't feel comfortable like assuming that it's true until I've proven it. So in the inductive step, you basically assume that Pk is true and go from there. So we're going to assume that Pk is true. Right, and I'm going to write my proposition with K plugged in. So that's going to be 1 plus 2 plus 3 plus K is K plus 1 over 2. So this is assumed to be true for now, okay? And we want to use this true statement to show that P at K plus 1 is true. Right. Okay, but I'm going to write the PK plus 1 proposition. So you go back to the original Pn, and you replace your n's by k plus 1s. Okay, so we have 1 plus 2 plus 3 plus ... and it's going to go to k plus 1, but I'm also going to say it goes to k and then it goes to k plus 1. So instead of making that k as part of the dots, I'm going to show it explicitly because it's going to help me in the next step. Okay. All right. And when I replace the n by k plus 1 here, I get k plus 1 and then k plus 1, which makes it k plus 2 divided by 2. Okay, so assume that this statement right here is true. This one is true, and somehow we need to use this true statement to show that the pk plus 1 statement is true. Okay, so these kinds of problems with sort of proving formulas of sums is done by substitution. Okay, so what we notice here is that this part of the left-hand side is exactly the same as this. Right? So these are identical. So because this expression is assumed to be true, then I can replace the 1 plus 2 plus 3 dot 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 plus k with this formula. So this is going to get plugged into here, but just the first k integers. Okay, so this gets replaced by k plus 1 over 2. Right, and notice that what's left there that hasn't been replaced is this k plus 1 over there. Okay, now this is in question. Okay, so we want to show this. So we don't know that this equality is true yet. Okay, so this side of the equation right here, this needs to be proven. Okay, so what I'm going to do now is sort of I replace that with the k plus 1 over 2 formula, copy down the k plus 1. We're going to do some algebra on this to combine it, and our goal is to show that these are the same. Right? So let's combine it. So we're going to find the common denominator. So this is going to be k plus 1 over 2, and then 2 k plus 1 over 2. We can combine these because they have the same common denominator. Notice that k plus 1 is a common factor, so we're going to factor it out. We get k plus 1, k plus 2 divided by 2. All right, now I look up and I see, yep, I got what I was looking for. I kind of transformed the left-hand side into the right-hand side. That means the pk plus 1 formula is true. So this is the end of it. This is the QED, quad era demonstratum, that says you ended the proof, you're done. You showed that the inductive step is correct also, and that's the end of the induction proof. Okay? All right, so that's it. That's the process. I'm going to do a few examples. So the types of examples, the types of problems that induction is really useful for is the first few examples we're going to see is proving formulas for sums. So sum of this equals that. So these are probably formulas that we've seen before. You might have seen in math before, but it's kind of like they were given to you. Mathematicians often don't like to just sort of be given formulas to use without proving that they're going to be true for all values of n in the universe that they're interested in. So this is kind of behind those formulas that you've been doing. Somebody has proven by induction that these formulas are actually valid for all positive integers. Okay, and so other kinds of problems that are good with inductions you'll see are some inequalities and also some divisibility problems. So is this expression divisible by this or that? Okay. All right. So let me go grab the example 2. I'll be right back. All right, so I'm back. So I grabbed the second problem, second example from the lecture sheet. And that says, conjecture a formula for the sum of the first n positive integers. Then prove the formula using induction. So what I want you to do is pause this for a second and try to come up with a formula for the sum of the first positive integers, odd integers. So like add 1 and 1 plus 3, 1 plus 3 plus 5. Kind of add, do a few examples and figure out, see if you see a pattern. And then come up with the formula and then prove it using induction. So this is sort of, we're not starting with the formula, we're conjecturing what the formula is. But try it out for a few minutes and then unpause and see what you got. All right, here we're back. Let's see how we did. So let's look at this, the sum of the first n positive odd integers. So first odd positive integers is just 1. And if I just have 1 and don't really add it with anything, that's 1. So this is kind of like the basis case. The second example would be if I have 1 plus 3. So here's the sum of positive odd integers. That's going to give me 4. Let's extend it. I have 1 plus 3 plus 5. So what's that going to be? That's going to be 9. 1 plus 3 plus 5 plus 7. So we're adding positive odd integers. So 9 plus 7 is 16. Okay, I'm already starting to see a pattern here, but let's do one more. 1 and 3 and 5 and 7 and 9. So I add 9 more and I get 25. Okay? I don't know about you, but these to me look like, right, they look like perfect squares. Okay? So I know I'm going to have the formula 1 plus 3 plus 5 plus 7 plus 9 and so on up to a certain point is going to give me n squared. Okay? So I need to kind of figure out what goes here. I know that the way to write an odd integer, you can do 2n plus 1. That's an odd integer because 2n is always even. 1 is, but if you add a 1 to it, it's going to turn into odd. But this doesn't have to be plus 1. It can be minus 1, it can be plus 3, it can be plus 5, minus 3, minus 5. As long as you're sort of taking an odd integer and you sort of be adding or subtracting something. Sorry, this is an even integer and you're adding or subtracting something odd from it, is going to, the whole thing is odd. All right, so to figure out what goes here, we could, let's say, test it with this last entry right here. So basically I'm trying to figure out how to write this in terms of n to make this last entry be equal to 9, right? So I know that 25 here is 5 squared. And so my n is equals 5. So if I say 2n plus 1, that's going to give me 11, which is not right. And if I say 2n minus 1, that's going to equal 10 minus 1, which is 9, which is right. Okay? So to fit with sort of the pattern that we've developed, this last entry right here needs to be, oops, I said 2n minus 1 and I wrote 2n plus 1. That's not right. Okay, so this entry, last entry right here needs to be 2n minus 1. Okay, so this is the formula that we are conjecturing. We figured that if we add positive odd integers, the answer is always going to be a perfect square, like with this pattern, okay? But just because I wrote down 5 lines and it's always a perfect square, it doesn't mean it's a proof. It doesn't mean it's always going to be n squared for any positive integers. Like a mathematician is not convinced that this is not evidence. So we want to prove it irrefutably, okay? So that's where induction comes in. Okay, so for the induction proof, we're going to do the basis step first, and then the inductive step. So the basis step, P1, okay, so this right here, like in my formula, this is my Pn. And this is my proposition over the universe of positive integers. So the basis step is P1. That's basically this right here. So basically, if I plug in n is 1, I start and end with 1, and I don't have any other odd integers. And on this side, on the right side, I get 1 squared, so I know that holds true. All right? Now we're going to do the inductive step. So the inductive step, we write two propositions. So we write pk and we write pk plus 1. Right, so pk is assumed to be true. And with that assumption, we need to show that pk plus 1 is true. Okay, so this is assumed to be true. Right, but let's write it. So we go to our pn formula and you replace the n's by k's. So 1 and 3 and 5 all the way to 2k minus 1 equals k squared. Right? And same for pk plus 1. We're going to go to our pn formula and replace n by k plus 1. So 1 and 3 and 5, dot, dot, dot. We're going to still write 2k minus 1, but then go on further. Okay, so if I plug k plus 1 in here, I'm going to get 2k plus 1. Because this 2k plus 2 minus 1 is 2k plus 1. Right, and this has to equal to, this is replaced by k plus 1 inside the parentheses squared. Right, so notice that this k plus 1 formula is the very similar sum of terms. So it's going to repeat over what we have before, but with this extra term right here. So we do that substitution again. We're going to notice that this is exactly the same as that. And because we assume that pk is true, that means this part is equal to k squared. The k squared goes in there, right? So we're going to write the pk plus 1 formula with that summation replaced by k squared. Okay, and this part right here gets copied down. Now this is in question. You don't know that that equal is valid until you show that this left-hand side is equal to k plus 1 squared. So we're not going to write it down. We want to transform this into that. And you can see easily that this is the case. These are the same because if I factor this, I get k plus 1 squared by factoring. And then I compare them, I see that they're the same. Okay? So you're transforming the left-hand side into the right-hand side to show that they're equal. Okay, I'm not